Alright, now that we have an idea of quadratics' place in history, let's actually do some stuff with a quadratic. So first of all, let's write out the equation ax squared plus bx plus c, and that's going to be equal to our y. So what does this shape look like just by looking at this equation? Well, we know there's a geometric way to think of it, and that is thus. It's a square. So let's only talk about this term first. So x. How does x change? So if I increase x a little, it will have an extra area of this. All right. But this is the point when we make a realization. We draw another square with a bigger area, and we increase that a little bit. The area we added on is just a different x. I'm going to still write the same x, but it's different. The change here is getting larger and larger as x gets larger. So the change in size grows as x, just the value of x. So the size of x at a point grows. Alright, so we know that we should get, depending on our size, a bigger change if we have a bigger x value. So that means that the slope, we're talking about change, a rate, the slope changes at every point. Now if we have a value of 0 and we add a small change, we're adding a change of 0. So the change in size, the immediate change in size is equal to 0. Now if we choose, let's call this x1 and x2. So how do we talk about those changes? Well, you can actually do something pretty nice here. So let's call this a change in x. Let's call this a change in x, just a triangle. Kind of like that triangle size, change in size. It's very useful notation. So the change in x should be all these values added together. You subtract the difference from the original value right here, this whole square, because you only want this whole piece right here that I'm coloring in red. So you only want that bit right there. So what you do is you take the whole area, which is x1 times x1, or x1 squared. That's added to delta x, this change in x times x1. Delta x times x1. This might get confusing because we have two x's occurring. This is change in x, this whole term. This is just our x1 point. And we have two of those because if you look, that's this area here and this area here. And last but not least, we have change in x times a change in x. Now, we don't really care about this whole thing. We only care about the change part. So we want to subtract the initial, this initial piece, which is x1 squared, and then we will also want to divide by the change in x, because dividing by the change of x, this is slope. It's the change in size, in this case, over change in x. So as we increase x, how does the size change? So if you notice, the x1 right here cancels with this x1. So we're left with 2 change in x, x1, x1, plus change in x, and there's 2 changes of x, and all divided by change in x. So if you notice, this x1, this change of x divides out, and this change of x divides out there. So we're left with 2, that's an x1 right there, sorry, it looks like I scribbled it out, and then plus a change in x. So it sounds like we're totally off topic. All I'm trying to do is quantify how much this changes at an exact point. So if we notice, what this is telling me is if we make our change infinitely small, if we make it immediate, if we talk about this direct point, because yes, if I go even a little bit bigger than a change of 0, we're going to have an increase of area. But we don't care about that small increase of area because we're talking about the immediate. Immediately, nothing happens to that dot. Now immediately with this guy, it changes a little bit in this direction and changes a little bit in this direction. So this change is going to be 0, a value of 0. So we get 2 times the x1 value. Now you can do the same trick for right here, and I'll just tell you the punch line, I guess. We get 2 change of x, 2. Just like this guy. So you can see if x2 is bigger than x1, then 2x2 is going to be bigger than 2x1. So that actually gives us insight on drawing this curve, as crazy as it is. Well, guess what? This a multiplies everything, and so we don't really care about it. It just multiplies times whatever values go below here. And a multiplied times whatever values these go here. And this guy, the slope is b, so it's always going to be the same slope. It's going to be linear as we know it. And this value does not change, and so it has no slope. So really, all the interesting stuff happens here. So you're going to get 2a times the x value. That's going to be the slope. So what does that tell you about the graph? So let's center the graph. Just ignore those terms for a minute. So we know the slope is 2 times the x value. We can forget about the a. The a is just some value here. It scales it up. So we know at 0, this will have a flat slope, alright? So it's going to be completely vertical on this graph. So we know we're going to have something like that. If we go 1 in ahead, we're going to get a slope of 2. A slope of 2 is going to look something like that. Now if we go 2 ahead, we're going to get a slope of 2 times 2, which is 4. That's a little steeper. And now if we go in the negative direction, we're going to get downward slopes. So going down in this direction. So at -1, we're going to get a slope of -2. And at -2, we're going to get a slope of -4. Now if you connect these lines continuously, these immediate changes actually tell you the shape of the graph. This is what we'd call a parabola. So that's how you get that shape. And that is also how it connects to this square. So that's just some quick calculus. Sounds crazy, but all we're saying is that the slope is, the immediate slope, I guess, is 2 times the x value at a certain point. That's an interesting takeaway, but actually tells you more information about how to draw the graph. Alright, let's move on. We know that every parabola is just going to be a shift of that, or a flip of that. If the a is negative, it's going to be, all the values are going to be negative each other, so we were decreasing this direction, now we're increasing this direction, and we were increasing this direction, now we're decreasing that direction. So it's just a flip if a is negative. So you can get all sorts of parabolas anywhere around here. So let's keep going here. Now let's answer a question about parabolas. So, well actually a question about quadratics in general. So let's make up one. Let's say x squared plus 3x plus 2. Alright, this one was inspired. So here's going to be the thing. If I give you that term, this y value is, if you remember, area of a quadrilateral. Area of a square, basically. So let's draw a square. Alright. Now it's not going to be a perfect square because we have x's changing and everything. But we know the area of it is y, because these two values multiply to equal this whole term. Alright? So here is method 1 of solving it. Method 1 is, you know that if you multiply this out, if it's going to look like this, you're going to have an x plus something and an x plus something over here. Alright? So if we, let's call those, no, let's keep those as squiggles to make this kind of fun. So we have squiggle, let's call it squiggle 1 and squiggle 2. So squiggle 1 times squiggle 2 is squiggle 1 times squiggle 2. Now x times x is x squared, so yep, so we know that this is definitely x and x. And then these other terms, this doesn't have an x and this has an x squared, so these terms have to add up to 3x. This is going to be squiggle 1 times x, and this is going to be squiggle 2 times x. Alright? If you're following along, all we're doing is we know that if we multiply we call these binomials. These are two-termed things, two things. The squiggle, with just some number, and x, and a different squiggle. So you can figure these out just by guessing, because you know that any two numbers multiply to become x squared. We get, these both have an x term, so we can factor that. And we get a squiggle 1 plus a squiggle 2. And then this last term on the end is always going to be those two squiggles multiplied. Alright, so if you check this out, the squiggles look pretty crazy. But this is actually telling you what two numbers multiply to be 3. Well, no, add to be 3, and what two numbers multiply to be 2. This should jump out at you. I mean, I intended it that way. If we're trying to get 3 and multiply to 2, well, we know that 1 times 2 is 2. That checks out. So that checks out with that guy. And 1 plus 2 is 3. So therefore, we found those two squiggle terms, so we can decompose this as that y value to its sides. So this first side is going to be x plus 1. Alright, yep. And the second side is going to be x plus 2. So we can say that this is the same as multiplying x plus 1 by x plus 2. So this is basically half of algebra for you. This whole thing right here, just decomposing these to go this way. Now the easy part is going this way, the hard part is going this way. Because sometimes things aren't this simple. Sometimes answering that question, what two numbers add and what two numbers multiply, gets a little tricky. And so we want to be open to other methods for solving this rather than just guessing. I mean, that's kind of what we did here. No, that is what we did here, I'll admit it. So, by the way, just because I already did it, why did we, what we call, factor it? Why did we factor? Well, reason one is, well, actually, this is almost the only reason. It's easier to manipulate and it tells you two things about the curve. So, let's forget about this for a second. And I'm going to say one thing. If y is equal to 0, the area is 0. Good? Yeah. So we're going to assume this for a second. So if the area is 0, it has no space on the graph. A line has an area of 0, a point has an area of 0, and a line this way has an area of 0. So y is, oops, drop that. Why is pointing that out any useful? Well, we can say that if x plus 1 has a value, that doesn't matter as long as x plus 2 is 0. Alright? We can say that, hey, if our values are the same, if x plus 1 and x plus 2 equals 0 at the same point, it's going to have no thickness, and so they're both going to be equal to 0, which answers the same question. Sorry, there's x plus 2 and x plus 2. There's not an x plus 1 and x plus 2 where it equals 0 at the same spot. So I'm just making up other functions. So, or you have the case where this y length, this x plus 2 right here, does have thickness. So that doesn't equal 0, it just equals some value. But this has no thickness. So x plus 1 equals 0. So the reason this is useful, thinking about it this way, is because you know that if you have two numbers multiplying and they equal 0, then this number right here equals 0. That gives you one of the values where it's 0 as a y value, and the other 0 as a y value is going to be when this guy's 0. It's when there's no thickness in in one of the directions. The other direction doesn't matter if the other direction has thickness. Now realize if we get this case where it converges to a point, then that is the only case. So we have what we call 1, 0. 1 point when the area or the equation, the quadratic equation, is equal to 0. That's 1, 0. And if we, in this case, we know that it would look like this one way and this the other way. So we'd have 2 zeros. That's the other circumstance. And then there's a third circumstance where you're never going to be negative. I mean, we're never going to be 0. That's weird. Unless you go into a complicated sense. Either way, solving for 0 is very useful, and that one property that either one of these could be 0, and so that gives you 2 x values for a 0 on the equation, tells you a lot about graphing one, and tells you a lot of information about studying one. So if you have this occur in, well, one thing that has parabolic shapes, negative parabolas, is if you jump. If you have anything going in the air, you can't really see that because we're kind of bird's eye right now, then its graph is going to be a parabola if you throw it up. It's going to have that initial speed, and then it's going to slow down, slow down. So you can find those 2 points where it equals 0 on the equation, where it hits the ground. Just by knowing how to factor or how to manipulate quadratic equations, because this is a quadratic equation. All right. So, by the way, just let's try to graph this really fast. It's going to be sloppy on purpose. So there's our axes. So we know it's going to be equal 0 when this guy is 0. So negative 1, right? Negative 1 plus 1 is 0. 0 times anything is 0. So negative 1 is one of those points. And the other point is going to be negative 2, because negative 2 plus 2 is 0 as well. So it's going to equal 0 of all of those points. And we know this is a positive parabola because we don't have an a value that's negative. So we get something along these lines. And this is going to be a rough graph. But I'd say that's great, actually. And then it has an intersection at 2, by the way. You can tell that just from here, because if you make the x values here 0, we're going to get a y value of 2. And you can see that's 0 on this curve. So those are basically the 3 important values. I didn't mention this one just because it's kind of trivial, it's kind of obvious, it's kind of clear from the equation what it equals at 0. Not necessarily this equation. This equation you have to do some think about, because you're not solving for 0 anymore, you're basically solving for 2. But this guy, very easy to just tell where the height is, where the intercept, we call this y-intercept and this x-intercept. Alright, that's a lot of info. But now, we're actually going to do the greatest bit of info for this whole explanation. Alright, and here it is. It's called the quadratic formula that accompanies quadratic formula. And this is something that scares teachers away from teaching it, because it's not pretty. Unless you think of it geometrically, which most people really don't. So we're going to do quadratic formula geometrically. Alright, this is a neat way of talking about it. So we know we could think of this idea of change geometrically, and that sped us up. We can do the same thing with quadratic formula. So the idea of quadratic formula is if I have an ax squared and bx and c, I want a way to solve for the zeros without just guessing, because guessing won't save my butt every time. Alright, so we're solving for when this graph equals 0. And sorry, one thing I forgot to note is that solving for 0 is useful, because if I'm solving for when this curve equals, let's say 5, let's say that's 5 on our curve, let's draw in black so it's more pronounced. So if I'm solving for a point 5 on this curve, let's call it, this is going to be y equals 5, and y is always 5. So finding this intersection is the same as finding this quadratic formula where we subtract 5, because that moves this graph up to 5. That's just a quick side thing. Oh, would be plus 5. You said equal 5. Yeah, it'd be minus 5. That's just a side thing. So technically finding the zeros is what you're doing no matter what point you're finding on the graph. So that's why that's useful. Let's forget about it for now. Alright, 0 is this whole guy. So let's write it geometrically. This is basically our y value. So we have a thickness of 0. Let's give it thickness anyway, though. We're going to pick an x that doesn't give this value of 0. So let's see here. So we have ax squared plus bx plus c. One thing we notice is that when we decompose that, it can be decomposed into 4 little parts, where these 2 parts right here make up the bx term, and this one part here makes the c term, and of course the main term shows up. However, one thing about that graph that's important to match is this is only x squared, and trust me, the equation is so much simpler to solve if this equation, if this is 1 here and this is 1 here, or if this is 1 here, same thing, somewhat. So we want our x squared term to be 1 here. How do we do that? Well, here's a very neat trick that just happens because we're solving for 0. If you divide every value here by a, 0 divided by a is 0. That's neat. It's like a trash bin in my thought. Then b divided by a is b divided by a. This is going to get messy because of all these variables, but whatever. We can deal with it. And ta-da, yeah. That's what we're going to get. So we can decompose this into a rectangle or square, however you want to think of it, of 4 parts. This is going to be our c part. That's easy to mess with. This is going to be our x squared part. Oh, it's not going to be a c part anymore because we do not have an a term. This is going to be our c divided by a part. Alright? So, yeah. These will equal 0 at the same part because it's just scaled down by a. That's why that 0 was still there. And this is going to be b divided by a times x. And this is also going to be b divided by a times x. But here's the thing. This is actually going to be a square. We want this to be a square. So technically, this is... technically this is a rectangle right now. And so there isn't really an easy way to solve that. But here is the trick we're going to do. We know we're solving for an area of 0. So this is equal to 0. Alright? So if we subtract a c divided by a, what we get over here is a negative c divided by a. This is a little confusing because we're talking about negative area. But trust me, negative area basically is the same thing. Now this is going to be equal to this rectangle where you removed that c divided by a piece. So this b divided by a, this is kind of the first piece, the second piece, and they add up to b divided by a. I'm being careful here. So now what we have is something that has potential at becoming a square. Because this c divided by a piece isn't guaranteed to fit in there nicely. In fact, it usually doesn't if you picked at random. And so by moving it to this side, we're happy campers. Because now we can put in our own piece that goes here. And so let's find that piece first of all. So if we have b divided by, this is actually going to be 2a, and this is going to be 2a. So these two values will add up to b divided by 2a times x. And b divided by a times x. And this is going to be b divided by 2a times x. And this is x squared. So we actually have insight now on what this piece should be. Because if this piece is x and this piece is x, that checks out for those x's. And now all we have to add is a b divided by 2a. And now add a b divided by 2a. So if we're going to add this piece on here, it has to be b divided by 2a squared. I'll just write that separately. Alright, so we're adding that to this side, and because we add it to there, we have to add it to both sides. There's the magic of algebra. So we add it to both sides. And now, if you know the quadratic formula, you should be noticing some very close parallels to the quadratic formula already appearing. So check it out. we know that this number squared, because this is literally a square with this length, the same length on both sides, that x plus b over 2a squared is going to be equal to all this stuff, c over a plus that little bit we added on. You have to be careful about that little bit being there. So now we can do this magical algebra trick called the square root. And so now we get, this is going to be just a little bit messy. Square root of, I'm going to put b squared. I'm going to expand this. It's going to be 4a squared. If you square that whole value here, b squared over 4a squared instead of 2a. And then that's going to be minus a c over a. Alright, and that's going to be equal to, since we square rooted, that got rid of this little guy up here. And so now we just have x plus b over 2a. And now here's where the fun stuff happens. Well, it's not any more fun than it has been. First step, let's combine the stuff in here. That b squared minus c over a all over 4a squared. Let's combine those. So a times b squared is ab squared. 4a squared times c is... Wait, why did I multiply by an a? We just want this guy to be 4a squared. So it's going to be b squared minus, we want to multiply by an extra 4a, so then it's 4a squared on bottom. So we're going to get 4ac, and now the bottoms match to be 4a squared. Now here's the beauty. If you square root this guy, the top doesn't square root nicely, but the bottom does, because 2a times 2a is the same as 4a squared. So square rooting that will just give you 2a. And then you're left with b squared minus 4ac. And that's equal to, let's see here, the x plus b over 2a. I'm just going to write x, and now I'm going to subtract the b over 2a to the other side. So what we've done so far is we had the extra piece, so this 0 area can be distributed nicely. So this is a square. Now we square root it to basically just give us this linear side and this linear side. Now we subtract that extra bit we added on to x, and we get, you can combine the denominators, and you get x equals, let's put negative b in front. Technically it's positive or negative square root, just because of how square roots work. A negative number squared is also positive. Yep. So it's negative b plus or minus square root of b squared minus 4ac all over, these both have a common denominator of 2a. That's the quadratic formula. And this plus or minus makes sense because you're going to have two values generally where the equation equals 0. Alright, thanks for watching. Use this formula all the time, whenever you want. Lots of people memorize it. You don't have to memorize it. You can just memorize how to prove it for yourself. Whatever. Alright, thanks.